Hello student, welcome back to our M.Sc First Physics Semester 2nd course, that is Atoms and Molecules, and our subject code is PSCT 122, and this is our 7th lecture. In our previous lectures we have covered the basic principle of NMR spectroscopy and also the theory of the NMR spectroscopy. Also we have studied about the NMR spectrometer, that means the instrumentation of the NMR and how we get the NMR spectrum with the help of different components assembly, and also we have studied about the NMR spectra. And now in this lecture we have to study the important process in the NMR, that is the relaxation process in the NMR. So we start with the relaxation process in the NMR. Consider absorption of electromagnetic radiation by a microscopic sample in which we observe the resonance. We know that generally there are two types of the samples, that is a macroscopic sample and microscopic sample. Macroscopic sample means which is a large in a size, and microscopic means which is a small in a size. That means this sample needs a particular arrangement to observe that sample or to study that sample, but here in general we consider the macroscopic sample so that we assume some, or we can make some assumptions to study the relaxation process in NMR. So consider the absorption of electromagnetic radiation by macroscopic sample in which we observe the resonance. That means if we place the macroscopic sample in a presence of external magnetic field and there is a absorption of electromagnetic radiation in NMR, obviously there is a radio waves radiations, and due to this absorption and all those things, that is the interaction between the nuclei of that sample with the external magnetic field in the presence of radio waves or radio wave radiation, then we get the resonance. Now for simplicity we shall consider a system whose nuclei possesses spin. That means for simplicity, that is for to eliminate the complications, we just consider the system whose nuclei possesses spin. Let N1 and N2 be the number of spins occupying the lower and upper states respectively. Here we suppose let N1 be the number of spins which occupy the lower energy level and N2 be the number of spins which occupy the upper energy level. So when the sample absorbs the energy, N1 and N2 should change and population difference must decreases with the time. We know that according to the Maxwell-Boltzmann distribution. In Maxwell-Boltzmann distribution, in equilibrium condition, the number of atoms or here number of spins in the lower energy level is obviously more as compared to the upper energy level, but in a presence of some other parameters like here the absorption of the electromagnetic radiation, this population gets disturbed and there is a population difference and this difference decreases with the time, but this is happen when and when there is absorption of energy by the sample. So there is a change in the N1 and N2 values, that is the number of spins occupying the lower energy levels and number of spins occupying the upper energy level. So the population difference must decrease with the time. Consequently, the electromagnetic energy absorbed by the sample should also decrease and ultimately become zero. Due to decrease in the population difference with the time, also there is a decrease in the electromagnetic energy absorbed by that sample and this ultimately become zero. That means there is a utilization of this energy and ultimately this energy becomes zero. But the intensity of NMR spectrum is usually independent of time, indicating a constant population difference. That means if we have a constant population difference with the time, then the intensity of NMR spectrum is independent on that time. So this is the important property of the NMR spectrum. Now in other words, there must be some mechanism in the system which allows the spin occupying the upper state to lose the energy by non-radiative transitions and return to the lower level. In general, we know that there is an absorption and emission process in any atom due to presence of external source of energy. If we consider a particular atoms, here we have a nucleus spin, then the nucleus spin which present in the ground state absorb the energy and it will excite to the upper state, and after some times they again de-excite to again and returns to its ground state. And in that process, when there is absorption, then definitely there is emission of some energy or photon. But if we have a non-radiative transitions, that means in this process we have a non-radiative transition, but there must be some mechanism for that. That means in order to conserve the energy, that means the absorption rate is equal to the emission rate or some utilized energy. So there must be some mechanism, and this mechanism is the relaxation process in NMR, because in NMR here we get after the spin flipping the non-radiative transition, but there is some mechanism. So this is the relaxation process. The transfer of energy from spin system to the other degrees of freedom is referred to as a relaxation. That means the atom gets relaxed again its ground state, but there is emission of energy or transfer of energy, and this process is done with the help of some mechanism, and this is nothing but the relaxation process. There are two different relaxation processes for common nuclei. So first is the spin lattice relaxation and second one is the spin relaxation. So these are the two very important relaxation process in a nuclear magnetic resonance. So first is the spin lattice relaxation. In the first, the spin is in upper state transfer the excess energy to the surrounding, that is to the lattice. This phenomena is called as a spin lattice relaxation, and the time required for the population difference to become 1/eth value, 1/eth times the population difference at t is equal to 0 and is referred to as the spin lattice relaxation time or longitudinal relaxation time, and which is denoted by T1. So the first relaxation process is the spin lattice relaxation. The name indicates that there is an interaction between the spin and lattice. Suppose we have a spin which is in the ground state and it absorbs some energy and it will excite, and after that there is a de-excitation for the after some time, and for that de-excitation there is a transfer of excess energy to the surrounding, but in the surrounding there is a lattice environment. So the transfer of energy between the from the spin upper energy state, the spin which is lies in the upper energy state to the surroundings, that means the lattice, and this phenomena is called the spin lattice relaxation, and the time required for the population difference to become 1/eth times the population difference at t is equal to 0, it is referred to as a spin lattice relaxation time. That means the time which required for the population difference, that is there is a population difference due to absorption of the energy, and this population difference equal to become, that is the value of population equal, this population difference must be equal to the 1/eth times of the population difference at t is equal to 0, and this time, the time required for this process is known as the spin lattice relaxation time, or simply we call it as a longitudinal relaxation time, and which is denoted by capital T1. So this is the spin lattice relaxation, but the value of spin lattice relaxation time is different for different materials. So T1 varies over a large range, being 10 to the power minus 2 to 10 to the power 4 second for solids and 10 to the power minus 4 to 10 second for the liquids. That means the spin lattice relaxation time is different for solid and liquids. For the liquid, the value of T1, that is a spin lattice relaxation time, is a 10 to the power minus 4 to 10 second, and for the solid, which lies in between 10 to the power minus 2 to 10 to the power 4 seconds. So this is the spin lattice relaxation, through which the energy gets transferred to the lattice. Now the second interaction is the spin relaxation. In addition to the spin lattice relaxation, relaxation of spin can also occur by a direct interaction of two spin states. It's called as a spin relaxation. That means we know that there are two spins, and this there is a transfer of energy. That means the interaction between these two spin states and the relaxation process occurs. So due to this interaction between the two spins, this relaxation process is known as a spin relaxation. Consequently, if initially the spin have a common phase, the phases will become random in the course of time. That means suppose we have a all those spins are in a same phase or in a common phase, but after time will goes, the phases will change due to the spin interaction, and this the dephasing, and the time required for this dephasing is nothing but this spin relaxation time. That means the dephasing time is known as the spin relaxation time, and transverse relaxation time, capital T2. That means there is a interaction between the two spins. That means there is a transfer of excess energy between these two spin, and the spin gets relaxed in the ground state again. So this is the non-radiative transition, but there is a energy transfer between the two spins, and the time required for this process and due to is known as the relaxation time. That is the time required, the dephasing time of the spins. That means suppose we have first all the spins are in a same phase, but due to the interaction the phase will changes, and due to this we get the relaxation process, and the time required for this dephasing process is known as a spin relaxation time, or simply we call it as a transverse relaxation, and which is denoted by capital T2. Again same like the spin lattice relaxation time, T2 has different values for the different materials. That is, for solids T2 is of the order of 10 to the power minus 4 second, and while for the liquids T2 is nearly equal to T1. That means if we consider the solid material, T2, that is a spin relaxation time is in the order of 10 to the power minus 4 second, but for the liquids the spin lattice relaxation time, that is a T1, and spin relaxation time, that is a T2, both have nearly the same values. The shape of the spectral lines depends significantly on the relaxation time. That means in the both relaxation process we have the two times. That is for the spin lattice relaxation process we have spin lattice relaxation time, and for the spin relaxation process we have a spin relaxation time, and the shape of the spectral lines in NMR is depend on these two relaxation times. When the relaxation time is very long, the lower state is being repopulated at the slow rate, resulting in the saturation. That means if we have a relaxation time is very long, it means there is a long time for the relaxation, or there is a long time for the transfer of energy. That means the relaxation time is a very long, then the lower state is being repopulated at the slow rate. That means the relaxation process is just for the repopulate the lower state, and when the relaxation time is large, then the population of the ground state or the repopulation of the ground state is a very slow rate, at the very slow rate, and due to this slow rate we have the saturation. And saturation means the number of spin state in upper energy level and number of spin states in the ground energy level. It may be same sometime when the relaxation time is very long, but therefore the relaxation time is small is beneficial. For the spin half system, let n be the total number of spins n of 0 and n of t with the population difference at the time t is equal to 0 and time t is equal to t respectively. Suppose we consider already macroscopic sample, and in that we have considered n1 be the number of spins occupying the lower level and n2 be the number of spins occupying the upper level. But if we add these two spins, we get the total spin, and the total spin is a constant and which is denoted by capital letter N. And here again we consider the n of 0 and n of t be the population difference at a time t is equal to 0 and at a time t is equal to t. Here we consider the time interval, that is from 0 to t, and according to that we get the different energy, different spin states. So here n of 0 and n of t. Now then the rate of change of the number of spins occupying the lower energy level, which is equal to Wn2 is Wn2 minus Wn1, which is equal to, here is a W is a common in both terms, so here we can take W outside the bracket, so W into N2 minus N1 and which is equal to minus Wn. Here if we have a spins, that is a N2 minus N1, and this quantity we can denote by the again new letter, that is a small n. So this is the difference, that is a population difference, and which is denoted by small n. So rate of change of spins which occupying the lower energy level is given by the this quantity. So here W is the transition probability per unit time for induced absorption or emission. We know that in relaxation process, first the most important process is the absorption or emission. So in the absorption, the nuclei get excited from the lower energy level to the upper energy level, and for emission the nuclei spin get de-excited from upper energy level to the lower energy level, and therefore the W is the transition probability per unit time. Transition probability means there is a transition between the upper energy level to the lower energy level or lower energy level to the upper energy level per unit time. This is the per unit time. So if we multiply this transition probability by the rate of the number of spins in the upper energy level and number of spins in the lower energy level, and if we subtract the number of the product of the number of spins occupying the upper energy level minus the number of spins occupying the lower energy level, we get the rate of change of number of spins which occupy the lower energy level. So this is the rate of change of number of spins occupying the lower energy level, and from this we get directly this relation. This is the equation number 1. Since n1 plus n2 is equal to n and n1 minus n2 is equal to n, here we have considered this quantity as n, and we know that the total spins are constant and which is denoted by n, that is n1 plus n2 is equal to n. From this we can calculate the value of n2, that is here n2 goes towards the right hand side and n1 goes towards the left hand side, then we will get n2 is equal to n1 minus n. So this is the value of n2, and substituting the value of n2 in n1 plus n2 is equal to n, we get, that means here we can substitute this value in this equation. So we get n1 as it is, the value of n2 is the n1 minus n, so this value is equal to n, again n as it is. Now here is the 2n1 or addition of this n1, so 2n1 minus n is equal to n. After that we can rearrange the equation for n1, so we get the n1 is equal to half capital N plus small n. So this is the number of spin states occupying the lower energy level. Now if we differentiate this equation, that means with respect to time, we get the again rate of change of number of spins occupying the lower energy level, and from that we get again the same equation, that means after differentiating we get the some quantity on the RHS side, and after that we can equate these two equations. So here differentiating with respect to t, we can write that is a dn1 by dt is equal to half dn by dt. Here the LHS is the n1, and if we differentiate LHS with respect to t, then dn1 by dt, that means this term, and after that on the RHS n, capital N is the total number of the spins, but we know that the total number of spins for a given system is a constant, so the derivative of n with respect to t is a 0, and only there is a derivative of n with respect to t is a left with respect to, or derivative of small n with respect to 2 is only left, so half as it is, and the derivative of small n with respect to t. So here we get the equation number 2. Now from equation 1 and from equation 2 we have the LHS quantity, that means this quantity in both equation we have same, so we can equate the RHS of these two equations. So from equation 1 and 2 we can write dn by dt is equal to minus 2wn, that means half dn by dt is equal to minus wn, and here we can put this half towards the RHS side, so we get this equation, that is dn by dt is equal to minus 2wn, and after integrating this equation we get the number of spin states at a time t, and which is related to the number of spin at a time t is equal to 0. So after integration with respect to t, here we get n of t is equal to n of 0 e to the power minus 2wt. So after integrating we get this quantity, and the time required for the value n of t becomes n of 0 divided by e is defined as the spin lattice relaxation time t1. That means the time required for value n of t, that means the number of spin states at a time t, to becomes equal to the number of spin at a time t is equal to 0, and the value is n of 0 by e, and is defined as the spin lattice relaxation time. That means the value goes from n of t to n of 0 by e, and this time is nothing but the spin relaxation time t1, as already we mentioned it. So therefore t1 is equal to 1 by 2w. So this is the relaxation time, and this is generally spin lattice relaxation time t1. So that is the spin lattice relaxation time is inversely proportional to the transition probability per unit time for the induced absorption. That means induced absorption means here we can incident the electromagnetic radiation, but in NMR generally radio waves radiation, and due to this there is a induced absorption, that is a excitation of the spin from the lower energy level to the upper energy level, and for this absorption we have the spin lattice relaxation time is inversely proportional to the transition probability per unit time. So here we get the relation between the spin lattice relaxation time and the transition probability per unit time. So this is the time t1 which is equal to 1 by 2w. So this is the very important time for the relaxation process. So in this way we have completed the relaxation process in NMR. Generally there are two types of the relaxation process, that is a spin lattice relaxation process and spin relaxation process, and according to that we have two times, that is for the first, that is a spin lattice relaxation we have the spin lattice relaxation time, and for the second spin relaxation process we have a spin relaxation time, and the time affects our NMR spectrum. That means if we have a large relaxation time, then the intensity, as already we mentioned here, that is if we have a very long relaxation time, the lower state is being repopulated at the slow rate and resulting in the saturation, and this affect our NMR spectrum. So the relaxation process is very important in the NMR spectrum. So in this way we have covered the two relaxation process in the NMR. Now In our upcoming video we have to start with the new topic, that is a very important topic in the NMR spectroscopy, that is the chemical shift. We know that, as already we mentioned, in ESR we get the splitting due to hyperfine structure, and in NMR we get the two peaks for a particular spectrum, or we get the just peaks in NMR due to the chemical shift in a particular compound. So the chemical shift play very important role in the NMR. So in our upcoming video we will continue with the chemical shift.